we have talked about kinetic energy being the energy due to motion. And we've used this formula, and strictly speaking, this formula is derived for a particle. And so if the particle's position is changing, then it has kinetic energy. But what about if the particle is spinning? Instead of its position changing, it's just spinning. For example, or a different one in any case, what if we have this toy here which has a propeller? What if the propeller is spinning? Now clearly the propeller has motion, it's spinning, there is clearly kinetic energy. And yet if we use this formula, because the propeller isn't changing its position, it would have no velocity, and this formula would say it has no kinetic energy, which is clearly wrong. So we need to account for this kinetic energy that's due to rotational motion, due to spinning. And so we have a formula for that. To begin with, this formula here, which is the kinetic energy due to the position changing, is called translational kinetic energy. And our new formula is going to be for rotational kinetic energy. So please note, we now have two different types of kinetic energy that we need to account for, just like we have two different types of potential energy that we are accounting for. We have spring potential energy and gravitational potential energy. And now we have translational kinetic energy and rotational kinetic energy. And this formula is 1/2 I omega squared. Omega is the angular velocity, and I is the moment of inertia. Now I talk about moment of inertia in the angular momentum video, but I'm also going to talk about it here. To be brief about it, the moment of inertia depends on the distribution of matter about the rotational axis. So in the case of this toy, the rotational axis is right in the center. And so what determines what the moment of inertia will be is just how this matter is distributed relative to that rotational axis. Right? Now, we are only going to be focusing on specific shapes. We have hollow cylinders, hollow spheres, and solid spheres. Those are going to be the four primary shapes we focus on. You do have a problem which deals with a spinning rod, and that one will be addressed in that one problem. But the reason I mention these shapes are important because the formula for the moment of inertia is dependent on what the shape is. So for example, if you're talking about a solid sphere, for a solid sphere, the moment of inertia can be calculated by doing 2/5 mr squared, m being the mass of the sphere and r, of course, being the radius. And if you have a different shape, like a hollow cylinder, there's a different formula. Those formulas are in the contents section of the homework. They're also on the formula sheet. Anyway, this is how you get the moment of inertia. This is a calculation you do. And the moment of inertia is important because it basically tells us an object's resistance to any change in its rotational motion. That's the idea. But this is all there is to rotational kinetic energy. It's really just the kinetic energy due to rotation. This is the formula right here. And you need to be able to calculate your moment of inertia generally. And so you'd want to look it up. If it's a solid sphere, this would be the formula. If it's something else, you look at the formula and you use that formula appropriately. And you need the angular velocity. That's all there is to it.